ओके, तो कल के लेक्चर में हमने ये सारे टॉपिक्स देखे थे जिसमें हमने इंट्रोडक्शन, डिफरेंट टाइप्स ऑफ ग्राफ, फिर एडजेंसी मैट्रिक्स और इंसिडेंस मैट्रिक्स, कंपोनेंट्स ऑफ ग्राफ और स्पार्सिटी और डेंसिटी। ये सारे टॉपिक्स हमने कल के लेक्चर में देखे थे। अब आज के लेक्चर में हम लोग पढ़ने वाले हैं अबाउट एंड वॉक। ये कॉन्सेप्ट क्या होता है, डिस्टेंस का कॉन्सेप्ट क्या होता है, what is the diameter of a graph, and what are the different structural properties of a graph. So this is basically covering your lecture number 6, what's our taught. So today we'll be covering lecture 6 mainly. Okay, so the first thing that we'll discuss is path, walk, and distance. So first of all, if I am making a node, if I am making a graph, so this is A, this is B, C, D, E, and
Vanshika, have you just started?
yeah, just that. This is the
Okay.
first topic.
Okay, fine.
Yeah. So I have made this graph and I want to know what is a path and what is a walk. I want to understand the difference between these two terms. Let's say, first of all, can any one of you tell me what is the path to go from A to F? What can be the path to go from this A point to F point?
A to B, B to E, E to F.
Is there only one option?
शॉर्टेस्ट पाथ बताने हैं सारे बताओ.
Sorry.
A, B,
A
C,
B
D, E,
C
F.
D E F.
Okay. So path is a kind of walk where we do not repeat any node. Here you can see you haven't repeated any node. Now, if I say, let's say there is a path in which I go from A to B to E to D to C to B to again E and then finally F. That means I've started from here, I went to B, then from B to E, E to D, D to C, D to B, C to B, B to E, and then I finally went to F. That means you can see here I have repeated myself multiple times. This is also repeated, this is also repeated. So when you are repeating yourself, when the nodes are getting repeated in a particular walk, then we call it as, then it is known as a walk, when repetition of nodes is allowed. Whereas in case when you do not repeat a node, then it is called as a path. So this is the basic difference between a path and a walk. Walk is, yeah,
You just once more repeat.
yeah. Walk is in which nodes can be repeated. When you're traveling from one point to another, you can repeat a node. For example, you are in a city, you are new to the city, and you do not know the way from one point to another. So it may happen that you are circling around the same point again and again because you don't know the exact path, right? So that case, what you will do if you have come from A to B, you do not know I can directly go from E to F. You take a big circle and then go from E to F. Okay, so you're repeating your path again and again. That is known as a walk. When repetition happens, it is known as a walk. And in case when there is no repetition, you can travel directly without repeating any node. That is known as a path.
Okay, I understood. Thank you.
Yeah. Now there is a concept.
Vanshika,
Hanji.
आई जस्ट जॉइंड लेट. मैंने अभी आपने जो कंसेप्ट एक्सप्लेन किया है वॉक और पाथ का वो समझ गया है, बट जो आपने इसके पहले
This is
डायग्रामेटिक
the first
रिप्रेजेंटेशन
topic.
चाहा है, हाँ जी, ये थोड़ा बता सकते हैं कि फिर से कि ये एग्जाम्पल पे कैसे आएगा पाथ और वॉक का?
Matlab, sorry, I didn't get your question.
आपने जो ग्राफ बनाया है तो
Hmm.
आप थोड़ा वो एग्जांपल रिपीट कर सकते हैं इसके लिए?
एक्चुअली शी वांटेड टू से कि ये इन्होंने बस ये पता चला इनको कि पाथ क्या होता है, वॉक क्या होता है बाय डेफिनेशन। शी डोंट नो अबाउट दैट
हाँ,
ग्राफ का कैसे इसको एक्सप्लेन
आई
करा है
वांट
आपने।
टू नो इट थ्रू एग्जांपल।
Okay. Here you can see this graph.
हाँ जी।
Huh. So I am asking you, how can we travel from A to F? So there are many possible combinations. One can be from A to B, B to E, E to F. Second can be from A to B, B to C, C to D, D to E, E to F. Okay? So in these both the combinations, none of my nodes are repeating. Hence, we call it a path. Now let's say I am traveling from A to B, B to E, E to F, E to D, D to C, C to B again, B to E again, and then E to F. So here what happened, I repeated my nodes. B to E I traveled 2 times. So when you repeat the nodes, it's called a walk. So this is the first topic that I have started.
ओके ओके ओके।
Now comes the concept of distance. So in the same question, if I ask you, let's say this was the first path and this was the second path. So let's say I want to know the distance of first path and second path. So distance is nothing but you count the number of edges you are traveling from A to B, one edge, B to E, second edge, E to F, third edge. So this is 1, 1, 1. Total edges are 3. So the distance for path 1 will be 3. Same way, the distance for path 2 will be 1, 1, 1, 1, 1. That is 5. So this is how you calculate the distance. So I hope this is pretty much clear. This is distance. Okay. Now let's move on to the next topic, that is diameter. Let's understand what is the diameter. I'll take 2 examples over here. The first example that I'm taking is, let's say this is one node. Okay. From here I have gone. This is a graph that is given to you, and you are told to find the diameter of the graph. First of all, the diameter, the definition of diameter of the graph is, it is the maximum of shortest distance between any point of nodes. Okay, what you do, you calculate all the shortest distance, and then you find the maximum of all the shortest distance. It is the maximum of shortest distance between any pair of nodes. So let's see how we can calculate it. What we do, this is a root node. We can see this R that I have written is our root node. If from this question, it's pretty much clear. Now, how can we find the diameter in this case? What I'll do, first from this root node, I'll walk one step ahead. So how many possibilities I have to walk one step ahead? Either I can go here, or I can go here, or I can go here. These are my possibilities. This is my first walk. Okay. Now let's go to the second walk. Um, So from this, after first walk, wherever you have reached, I have reached to this node. Here I have reached here. Now from this point again, I will walk one step ahead. So I have these many possibilities to go one step ahead. So this blue color is my second walk. Okay. Now there are more possibilities. So I'll go another step ahead. So from here, let's say I am going here. This is my third walk. Here you do not have any option, so we can leave this. So this one is my third walk. Now moving on, I'll see whether I can go forward. Yes, from here I have an option. So this last one becomes my fourth walk. So what was the maximum number? What was the end number I found? So my end number was fourth walk, right? To complete the entire graph, I needed four walks. So here I can say that the diameter of my graph, of this particular graph, will be 4. Because I needed to reach the end node, I needed to travel I need to travel at least 4 distance. Like if someone is blindly asking you from node R to node X, X could be any node. It's no, you do not know about it. So if you know the diameter, you can say that in minimum 4 walks, so you will reach that particular X node. It cannot exceed 4 walks. Okay, so this is the role of diameter. Now, one case was this when you have a tree sort of diagram or tree sort of network. What if we have a normal network? So, in case of normal network, let's take an example. Let's say this is A, B, C, D, and finally E. Now, if such a scenario is given, if such a scenario is given and you are asked to find the diameter. So I'll use this definition that I have said before. What is the definition? First, I need to calculate the shortest distance between all pairs of node. Okay, so let me first make all pairs of node. What will be the pairs I'll get here? A to B, A to C, A to D, A to E, then I'll get B to C, B to D, B to E, C to D, C to E, D to E. These are my pairs that I'll be getting. Now let's calculate the shortest distance between these pairs. So from A to B, can anyone tell me what will be the shortest distance to travel from A to B?
It's AEB. AEB.
Yeah, so the distance will be 2. AE, one edge, EB, second edge. So the distance will be 2. From A to C again, the distance will be 2. A to D and then D to C.
Mhm.
A to D, the distance is 1.
But I won't understand this like ये जो आपने किया है ना A to B, A to C, A to D, A to E, B से C, B to D, ये कैसे किया है?
We are making all possible pairs that are possible. We have 5 nodes, so number of possible pairs will be
Okay.
मतलब जितने भी pairs you can make from this graph. If it's a
Okay.
bigger graph, there will be more number of pairs.
इसका कोई फॉर्मूला है क्या कि लाइक अगर इफ द नोट दिस मच ऑफ द एजेस आर देयर देन
बस
इतना हो?
पेयर्स बनाने, अब ए का पेयर बी के साथ बना लिया, एक का सी के साथ, एक का डी के साथ, एक का ई
हाँ
के
हाँ,
साथ।
ऑल पॉसिबल समझ गए, ठीक है।
हाँ, यस। Next, A to E will be 1. B to C ka distance will be 1. B to D will be 2. B to E will be 1. C to D 1. C to E will be 2. And D to E will also be 2. So we got all the shortest distance between all possible pairs. Now what you have to do, you need to find the maximum value, right? What is the maximum value amongst these? So 2 is the maximum value. So therefore the diameter of this graph will be 2. I hope this concept is clear of diameter. This was example 1 and this is example 2. If you have a tree kind of structure, this is the method of finding the diameter, first one. And if you have a simple graph kind of structure, the second one is the method to find the diameter. Is this part clear?
So this we will call as maximum walk or path.
This is diameter. This is not walk. This is not path. Diameter. It's another property. Like walk is a property, distance is a property. This is also a property. And of course, this is a path because you are not repeating anything. When you are
हाँ,
going from A to B, you're not repeating anything. So this is not a walk. This is a path.
path ना, okay.
Okay. Uh, Moving on to the next topic, that is structural properties. Now, this is kind of lengthy. So in structural properties, we'll be visiting different properties of a network. So the very first property is triangles.
Vanshika, 1 minute.
Hmm.
So the previous topic. So for every two pairs, we are taking the shortest distance, and to get the diameter of the whole graph, we will take max of what is the maximum shortest path that we have achieved in
Ah,
all the pairs.
yeah,
That will be our diameter. Okay.
yeah.
Okay. Thank you. Thanks, guys.
Now, next we are studying about structural properties. So in structural properties, the very first property that we'll be studying is triangles. So let me make a simple example of triangles. So this is what basically a triangular node looks like. Okay. So if a node has more number of triangles, we can say that the clustering coefficient of particular node is very high. Like for example, if I talk about this particular node, let me color it red. So it has 1, 2, 3 triangles attached to it. So the clustering coefficient, of course, for this particular node will be high compared to, let's say this node. This node only has 2 triangles attached to it. Okay. So first of all, when we are discussing about triangles, we go to a term called as triadic closure. So what is a triadic closure? If A to B is connected and A to C is also connected, then there is a very high chance of B to A being connected to each other. This is what this triadic closure says. So here, how you can define whether a particular graph is highly connected or highly like have more number of triangles or less number of triangles. For that, we use a term known as clustering coefficient. Now, what is clustering coefficient? Clustering coefficient can be defined as number of triangles divided by possible triangles involving a particular node. Okay. So let's say if a node has k neighbors, I am talking about a node. Let's say the name of the node is A. If a node A has k number of neighbors, then what will be the possible triangles that can form from these k number of neighbors? To form a triangle, we need three nodes, right? Then only we can form a triangle. First node is fixed, that is A. So what you need two more nodes. So out of these k neighbors, you have to select two nodes. So to form a possible triangle, to form a possible, all possible triangles will be simply KC2 because we already have one node with us. That's why we are not selecting three nodes. We already have one A node fixed. We only need two more nodes from the neighbor. So that's why all possible triangles will be KC2. And simply you can put the values here and calculate. Now let's try calculating it. For example, let's say this is our A node. This particular blue dot is our A node. Now if I want to calculate the clustering coefficient of this A, how I can calculate? First of all, I'll count how many number of neighbors it has. So it has 1, 2, 3, 4, 5, and 6. 6 neighbors are there. So the value of Ki will be 6. Now, what will be the value of possible triangles? Possible triangles will be 6C2. And in the numerator, you have to write number of existing triangles. So in the neighborhood, how many triangles exist? Currently, there exist 1, 2, 3. 3 triangles. So your clustering coefficient for this A node becomes 3 divided by 6C2. I hope this is clear.
How come it is 3? Can you repeat?
Sorry.
6C2, I understand. 3. How come it
We
is?
just counted how many triangles actually exist.
ठीक है.
Now, if the clustering coefficient is high, this means your graph is having more dense triangles. And if the clustering coefficient is low, that means you have less triangles. So just simply we can write it as, if the clustering coefficient is high, that means more dense graph you have. If the clustering coefficient is, let's say, 0, that means no triangles exist. And if say clustering coefficient equals to 1, that means we have a complete graph. What is a complete graph? Complete graph is a graph in which every node is connected to each other. Let's say if we have four people in a room and if each four of them talk to each other, that's known as a complete graph. Okay, so same way, if all nodes are communicating with each other, not communicating, they are connected to each other, then we can say it is a complete graph. So how you can numerically see that? If you get the clustering coefficient as 1 for a particular node, that means the surrounding neighbors and that particular node forms a complete graph. Now the value of this clustering coefficient will always be in between 0 to 1. It cannot be greater than 1, nor it could be negative. Any doubts regarding this triangle concept?
So CC can be 0 or 1, cannot be negative.
It it can be in between 0 to 1.
Okay, in
मतलब it
between
could
0
be
to 1. Okay.
0.5, 0 to 0.2,
Uh-huh.
any.
Yes.
Huh.
But cannot be negative, right?
No, it cannot be negative because you are counting things. You are counting number of triangles.
So
Counting
how it
cannot,
would be?
it
Uh-huh.
could not,
True.
never be.
Vanshika, we calculate this clustering coefficient at the node level, right? Uh,
Yeah. Actually, clustering coefficient, I'll again come back to this topic later on because here we are talking with respect to triangles. When I'll again come back to this clustering coefficient, then at that time I'll talk with respect to nodes when triangles do not
so,
exist.
so when we are, let's say, when we are calculating clustering coefficient, so we are going to analyze a node itself, right? Like,
Yes, actually there are two types of clustering coefficient present. One is local clustering coefficient that is for individual nodes, and one is global clustering coefficient that is for the entire graph. So we'll come back to that topic in detail after discussing all the structural properties. Like that is, I think, our second last structural property that we will discuss.
okay, okay.
Currently, we are only focusing that if we have triangles, how we can calculate clustering coefficient. Any other doubt in this? Okay, so let's move on to the second structure.
Vanshika,
Hanji.
when we say that the graph is complete, so which node will take, like in terms of which node you will say that any.
Let's say any node. Let's say this is a node. Okay, it has four neighbors. Now, let's say this node is connected to all other nodes. This particular node is also connected to all other nodes. It is also connected to here also. And that goes for every other node. Everyone is connected to every other node. So in such case, we say it's a complete graph. It's not possible for me to draw right now. Sorry. I take a simple graph. Let's say a triangle. Okay. If I draw a triangle like this, so here my first node is connected to both other nodes. Second node is also connected to both other nodes. Third node is also connected to other nodes. This is a complete graph.
No, I was just thinking like in particular graph, there
Hmm.
may be a possibility that for one node the coefficient is 1,
Hmm.
and for some other nodes it is not 1. So
Correct.
still we will say that that graph is
We
complete graph.
never, no, we don't define it for a graph. What we can say, let's say this is a graph. Okay. So for only this
Mhm.
much part, we have a complete graph, right? This is not a complete graph. So you'll just point it out or mark it out and say that this has a clustering coefficient 1.
Okay.
Okay. Now moving on to the second structural property, which is centrality. Second structural property, centrality. What is centrality? Centrality is basically if I have a node here, so how many nodes are connected to me? This is what centrality is. So this is my node A. So if I want to find out the degree centrality of A, so what will be degree centrality? It will be nothing but number of nodes connected to A. So there is 1, 2, 3, 4, 5. So my degree centrality for A will be 5. So this is the case for um, undirected graph. Now, if I talk about a directed graph, so in that case, what happens if this is my node? So in directed graph, of course, I'll have some outgoing signals or some outgoing nodes and some inward nodes, right? So in this case, how you define your degree centrality? Let's say I want to define my degree centrality for A. So there will be two degree centrality. One will be outward degree centrality and one will be inward degree centrality. So for A, how much is the outward degree centrality?
Two.
It's 2.
3. Huh?
Outward
It's
is
two.
2
Inward.
Outward is two.
and inward
Outward
is
is
3.
three.
Hmm.
So this is my degree centrality in case of directed graph. So basically what centrality measures in case of directed graph, how much influential you are. If we are, let's say, analyzing an Instagram account, the how much you influence people, how much you influence people can be calculated using the inward graph. Okay, number of people following you means if that is more, that means you are influencing more number of people. So centrality is how much influential a particular node is. This is what we are trying to calculate. So centrality is how much influential a particular node is. Okay. Now,
फॉलोअर्स के काउंट बता रहा है ये।
हाँ, एक तरीके से ऐसे समझ लीजिए। आउटवर्ड मतलब आप कितने लोग को फॉलो कर रहे हैं, इनवर्ड मतलब कितने लोग आपको फॉलो कर रहे हैं।
ओके
Now, there comes a concept of closeness centrality. Now, what is closeness centrality? It is nothing but sum of inverse of shortest distance from every node. Let me repeat it. Sum of inverse of shortest distance from every node. So this is what closeness centrality means. Now, how can we calculate this? Let us see. So if I want to, let's say I have a graph. And this is my point A, and this is my point B. So let's do one thing. Let's first of all calculate for point A. So for point A, I need to calculate the shortest distance for every node. I have to start from A. Let's say this is my first node where I need to reach. This is my second node, this is my third node, and so on. So for the first node, how much distance I need to travel from A to this first node? It is 1. From
One.
A to this first node plus from A to the second node, again 1. A to this third node, 1. A to the fourth node, 1. plus. Now from A to this particular node, let's name it A, small a. A to this small a, I need to travel 2. A to the small b, again 2. To C, again 2. To D, again 2 distance. Same way for E, F, G, and this B. I have to travel 2 distance. E, F, G, and B. So total, if you sum it all, you will get as 20. So A is equals to 20. Correct? What I have done? I have done sum of shortest distance from every node. Now to find the closeness of A or the closeness centrality of A, what I'll do, I'll just inverse this value. So closeness centrality of A will be 1 by 20. Now in the same way, can you try for closeness centrality of B? Like for B, what will be the closeness centrality?
One plus one, like one year, I guess. Like
1 plus 2 plus
two,
2
two plus two,
2 plus 2. Okay.
plus 3 plus 3 plus
How many?
3. 3
3 times 3
three in one, yeah, three times three,
and
4 4 4 4. 6 times 4.
six times four, yeah.
correct 6 times 4. So if you add it all up, this becomes 38. So the closeness of B will be 1 by 38.
But Vanshika, how do we define this like closeness, centrality in words, let's say?
Yeah, I'm coming to that. So if you calc once you calculate the closeness, what we can say is here bring it into decimal. So what will be the decimal of this? It will be 0.05, right? And this one will be this one will be 0.02.
0 to
0 to
6.
6.
Ah, so we can see that the closeness of A is higher than B. So we can comprehend that to go from any node to B, it will take more time compared to going from any node to A. So the time consumed to go from any node to B will be higher than A. So this is what we uh, deduce from this. Because the closeness of A is higher, that is why time to reach A is faster as compared to time to reach at B.
Can you repeat this last point again?
Because closeness of A is higher than B, therefore the time to reach A is faster than the time to reach B. So any doubt regarding centrality or closeness?
What we are saying, time to reach to A or time to reach to any other node from A? The- बात तो same ही है.
हाँ,
Which one is official?
time to reach from any other node to A. Actually, there is no official definition iska. It's
Okay.
just an interpretation. Whatever you write is correct. Next topic. Let's move on to the next topic then. Next one is betweenness. Betweenness means for a particular node you are checking that in how many shortest path a particular node is coming in between. For example, let's make a graph. So this is A, B, C, and they are connected something like this. Okay. Now, first of all, betweenness is how many times a particular node is coming in between when you are traveling from one point to another. So here you can see if you travel from B to G, A will come in between. If you travel from, just a minute. Hello? Huh? Yeah, I'm so sorry. So if you are traveling from B to G, so what will be the shortest path from B to G? It will be you have to go from B to A and then A to G. If you're traveling from B to E, let's say, again you have to first go from B to A, then A to E. From C to G you have to travel, then again C to A, then A to G. So betweenness is the measure of how many times a particular node will come in between of your shortest path. So we can calculate this betweenness using a formula, that is number of shortest path from A divided by total path which do not have A as their start or end point. This will be your betweenness of A. Let's try to solve this so that we can get a clear idea. Okay. First of all, if I want to calculate betweenness of A, I need number of shortest path from A. So how many paths will pass from A?
It's B A G C A F D A F, then again E A C F A C and G A C.
So there will be total 9 paths.
Mm-hmm.
BAE, BAF, BAJ. Same CAE, CAF, CAG. DAE, DAF, DAG. Total we have 9 paths. Okay. Now in the denominator what we want total paths which do not have A as their start or end point. So you'll make all possible combinations that you can make here. Just condition is you cannot have your start or end point as A. So what will be the possible combinations? It could be B to C, B to D, B to G, B to F, B to E. Then from C, if I go C to E, C to F, C to G, C to D. Then from D, D to E, D to F, D to G. E, say if I go E to F, E to G. And finally F to G. So total I have 15 possible combinations.
Oh, ये मुझे समझ नहीं आया है, इसमें ए इंक्लूड नहीं करना है, राइट?
ए स्टार्टिंग और एंड में नहीं हो सकता, बीच में तो होगा ही। मतलब जैसे मैंने पाथ
अच्छा।
बनाया, पहला पाथ है बी टू सी, ठीक है, दूसरा है बी टू डी, तीसरा बी टू ई, बी टू एफ, बी टू जी, सी टू डी, सी टू ई, सी टू एफ, सी टू जी, डी टू ई, डी टू एफ, डी टू जी, ई टू एफ, ई टू जी, एफ। ये हो गए 1 2 3 4 15, टोटल 15 पार्ट्स वी हैव। यहाँ पे in this anywhere we are not seeing that our starting point is A or ending point is A. This was only the condition. A cannot be the start or end point. So this will be a measure of betweenness for it.
And Vanshika, what about like number of shortest paths from A? How is it 9?
Huh. So now total paths you have got these. Now in how many paths you are finding A in between? When you're traveling from B to C, is A coming in between? No. So this is
Directly no.
cancelled. Shortest path only we want. B to D also, A won't come in between for shortest path. B to E, A will come. B to F, A will come. B to G, A will come. C to D, A will not come. C to E, A will come. C to F also, C to G. D to E also, A will come. D to F also, D to G. E to F you will not get A, E to G you will not get A, F to G you will not get A. So how many cases you are getting in A? 1, 2, 3, 4, 5, 6, 7, 8, 9.
ओके। वंशिका, वन मोर थिंग,
हाँ,
लाइक अगर हम बी से ई करें कहें और ई टू बी कहें, इट्स वन एंड सेम थिंग, राइट?
yes,
ओके।
because this is undirected.
हम्म। इन केस ऑफ अनडायरेक्टेड ग्राफ, ठीक है।
Any other doubts in betweenness?
वंशिका, आपने स्टार्टिंग में एक डेफिनेशन बताया था, इसका आप एक बार फिर से रिपीट कर सकते हैं?
Betweenness is like what I said. For a particular node, nahi, betweenness is how many times a particular node will come in between shortest path of any two nodes. मतलब वो कोई definition नहीं था, that I only said. It's not a definition written somewhere.
Uh, why we are calculating it? Like any.
It's one of the structural properties to define a particular node. आप मतलब betweenness से आपको क्या पता चलता है कि कोई भी दो चीजों को कनेक्ट करने के लिए कौन सी नोड पे आपको बार बार जाना पड़ रहा है, तो वो नोड आपकी हाई प्रायोरिटी हो जाती है, राइट?
हम्म।
So when
ठीक।
you are working on a big social network, so at that time, all these properties come into picture: closeness, betweenness, centrality, triangles. Triangles tell you about communities, how strong a community is. Okay? So like this, these different structural properties signify something when we go further.
हम्म। ओके।
Okay. Moving on to our fourth structural property. The fourth one is degree centrality. We already did degree centrality when we were discussing here. So we have already done. Let me show you 1 2 more examples of that so that we can get a more clear picture of that. Degree centrality. Now here, let's say I have a graph. Okay. And I want to find my degree of each point. So can anyone tell me what will be the degree of this A point?
Two.
It's 2.
Correct. 2. For B,
Two.
B
It's
again
2.
it will be 2. For C,
Yeah, it's 1.
Three.
3.
Three.
For C it will be 3. It is connected to 3 nodes. And
Okay,
for
huh.
D it will be 1.
1.
So this is degree centrality. Degree is nothing but number of connected nodes. Okay. Now what happens? Uh, if I want to define my graph more properly, like where uh, from degree I can like here if I am saying my degree of C is 3. So whether C is dense or not dense, how can I find that out? So for that what I do, I normalize this graph. Normalize this graph and I divide it by what I do to normalize a graph. Whatever degree I have, I will divide it by maximum possible edges. Now, what is maximum possible edges? This is nothing but n minus 1. N is our number of nodes. Okay. So for example, abhi currently this is a very small graph. So there is no role of normalization that you can see. But for example, I have a graph which has 11 nodes. Okay. If I have a graph which has 11 nodes and my degree centrality of a node A is 9. Okay. Then I have a graph which has 101 nodes and my degree centrality of a point A is 9 here also. So in which graph, graph 1 or graph 2, which is more dense? In which graph A
One.
is more dense?
Graph one.
Graph 1, because
Yeah.
only in 11 nodes you have 9 degree centrality. But here, if you see, for 101 nodes you have 9 degree centrality. So it is worthless over here. Whereas here it is signifying density. So how can you calculate this? Like here, so I knew my total nodes, so I could easily calculate it or I could easily visualize it. Now, if you are comparing both large numbers, so to compare this density, what we do, we normalize our degrees. So to normalize degree, we simply divide it by the maximum possible edges. The maximum possible edges can be given like n minus 1, where n is a node. So if I want to convert this graph into normalized form, so this will be, it was 2 here, 2 here, 3 and 1. So I need to divide it by maximum possible edges. So how many nodes I have in this graph? I have 1, 2, 3, 4 nodes. So this will be 4 minus 1, that is 3. So my normalized form will be 2 by 3, 2 by 3, 3 by 3 and 1 by 3. This is my normalized form. So we did nothing, we just divided by n minus 1. We first calculated degree centrality and then divided it by n minus 1. I hope this concept is pretty much clear.
N is the number of nodes, right?
N is number of nodes.
Okay, got it.
I think we should stop here uh, because we have.
Vanshika, so if we have, let's say we have a triangle,
Huh,
so in that case, the nodes are going to be three, and then even the edges are going to be three, right?
huh,
Like maximum possible edges are three
huh.
in this case. So
So for this one,
how will that justify this n minus one thing?
see, for let's say for this node A, what will be the degree?
Two.
2. And what will be n minus 1?
2.
2. This is coming as 1. 1 means maximum dense. Each of them you will get 1 because it is maximum dense. What does maximum dense means? Means that particular node is connected to every other possible node in the graph.
Okay. So again, it is like the maximum will be one and minimum will be
0.
zero.
Yes.
Can we say that? Okay.
Whenever we are reducing, normalizing it, normalization generally means that we are bringing it to the range of 0 to 1 or minus 1 to 1. In this case, 0 to 1 because it cannot be negative.
Yeah. Okay. Okay. Fine. In this case, n is the number of nodes, like
Yes.
total number of
N
nodes.
is
No?
total number of nodes.
Okay. Okay.
Uh, so I suggest we'll stop here. Now, in structural properties, there are 4 properties left. One is clustering coefficient that we already studied, but we'll go a little more deeper into it. Second, next is click, then plex, and then core. K-plex, K-core, click, and clustering coefficient that we'll see tomorrow. And after that, we'll start with sign networks.
लेक्चर 4, 5 एंड 6 का कंप्लीट हो गया वंशिका?
6 is almost completed.
ओके
4, 5 we have covered yesterday only. Now
ओके
lecture number 7 is क्या बोलते हैं practical पूरा network X के बारे में था. So
ओके
that you guys can see it on your own and rest everything to I'll cover. So I think total we have 20 lectures that we have to cover because total duration of the course was 10 weeks. So from that we have covered 6 lectures, 14 more to go. Any other thing that you would like to ask?
Thank you so much.
Thank you.
थैंक यू वंशिका.
Thank you, Vanshika.
तो
Thank you.
And
जो प्रैक्टिकल वाला है लाइक लेक्चर
हाँ,
7 उसका नोटबुक है क्या हम लोगों के पास? लाइक डिड ही शेयर?
that I'm not aware. You can check on Moodle once. नहीं तो उसका recording is available on this यहाँ पर
अच्छा अच्छा अच्छा.
यहाँ पे ये वही खुला हुआ है. If you click here,
हाँ
the
हाँ हाँ.
recording is available. Okay, then I'll end the session. Bye. Good night.
बाय बाय. गुड नाइट.